Hello everyone, I'm Youssef, SHAMAS, PhD student in the LMN laboratory at the Unsaturated Normandy, and with collaboration with the LOMC laboratory at the University of Le Havre, Normandy, I will present you today to my PhD research about the liquefaction potential of unsaturated soils. What is liquefaction? It's an disastrous phenomenon that can happen inside the soil, and the best way to demonstrate it is to show it to you visually. I will have our building here as a visual demonstration to a building, and we have the unsaturated soil in our container. We have the soil here. You can see the difference in the color where it's the unsaturated part where is only air and water and the soil. This is our building that we will build in our soil. As many of the countries construct their buildings directly on the soil without taking any precautions. As liquefaction occurs during an earthquake, we will use this to tap on the container to simulate the vibrations of an earthquake. As you can see, the soil around the building start to saturate directly. That will eventually lead to liquefaction, meaning that the sand will start to act as a liquid. The building itself will resist the vibrations, whereas the soil particles will lose their connections and the sand will lose its strength, which will cause the building to sink inside the soil. You can see here that the building starts to tilt with respect to its initial state. This is because we had in the beginning small difference in the saturation degree inside the sand around the building, and this caused one part of the sand to liquefy before the other, which led to this tilt. As you can see here in our slide, for a loose soil in fully saturated state, meaning that we have only soil and water, we have it in underlying conditions where the water cannot escape, as the case during the earthquake that happens rapidly. This will cause the water pressure to increase rapidly, leading to the loss in the connection between the soil particles and the occurrence of liquefaction. This case is well known in the literature for fully saturated soils, but recently we have found that this dangerous phenomenon can occur in unsaturated soils as well, where we have the soil particles, we have water, and we have air inside the water. As we are in underlying conditions and as the load is applied, the water pressure will increase, same as before, but this time starting from a negative pressure that we call suction, because we had the air inside the water. This pressure increase will reach the initial applied effective stress, causing the soil particles to disconnect and lose their strength. And this is what we are searching for. What is the limit of unsaturation that should be in the soil? At what limit the air should be in volume with respect to the water, so we will not have the liquefaction phenomenon. To do this, we have our research on the triaxial apparatus that we will use to duplicate the same phenomenon that occurs inside the soil at different depths, so different consolidation, confining pressure. And to do a confining pressure, we have our soil, which is in the yellow membrane that is found here inside the cell. And around this yellow membrane, we have the water that we will use to apply the confining pressure on the soil. And inside the membrane, there is the soil that we will saturate or desaturate depending on our need to duplicate the phenomena. And we will apply using a piston the dynamic load on the sample, positive and negative, using a funnel to liquefy our sample. We already know that there are different methods to solve this problem, but we have to understand when it happens, why it happens, what are the factors that we can play on and to avoid this liquefaction phenomenon. For example, we have the saturation degree, how much water there is, how much air there is inside the soil. For example, the confining pressure, the consolidation, how much our soil is condensed, and for example, the density of the soil, for example, also. All these factors we have to study in many different ways, and that's what we do in our laboratory, just to define the threshold at what level the soil will not liquefy. And as we know this threshold, we can use the best precautions to avoid the liquefaction phenomenon in unsaturated soils. And thank you.